Okay, let's go. Hello, everyone. Welcome back to the stream. Sorry for being a bit late this evening. So, on Tuesday, we did some work on fixing the export of things that we had removed last week. Because last week we've been working on finally making a proper main for our compiler and therefore and finally having a proper pipeline. But as a result, we removed all of the debug exporting of things, and on Tuesday we fixed some of this. This included finally generating, how is it called? I don't remember. I think it's in debug. There we go. We have generated a rendering of the IR of a simple program. And if I run dot from that file, I should be getting, there we go. I am getting the visualization of the IR in dot form. Now, the whole reason why last week I worked on having a proper pipeline for the project, this new compile module, is I want to add built-in functions to the compiler because I want to be able to test our program. Actually, how does it render in Emacs? Can I zoom it? No, I can't zoom it. That's not the best visualization tool as a result. I want to take our program that is currently only changing the memory of the interpreter, and I want to add a print there at the end. And at the end of main, and I want to add a read at the beginning of main to take the argument to the Fibonacci function as a on the standard input. To do that, we need to have built-in functions. So what we are going to work on this evening is the prelude, the functions that will always be included in every single module. And we have several options and several problems with how we want to define it. One of the main options we have is, do we want to bundle it at compile time of the compiler time, so that when we run the compiler, we don't have to go parse and read the prelude and compile it like any other module. We can just use the fact that it was pre-compiled when the compiler was compiled. Or do we treat the prelude like a library and it gets loaded every time we compile anything? Another problem we have is some of the functions we're going to define in the prelude, the built-in functions, cannot be defined in terms of the language. For instance, print this to the standard output is not something I can express with other functions, since there's nothing in the language that allows this. So I think to solve that second problem, I'm going to use the same thing that Haskell does, which is I'm going to define functions with the right name and the right type, but with incorrect bodies that happen to compile. And the correct implementation will be substituted at linking time. So instead of actually compiling down to binary or bytecode in our case, we'll substitute the correct bytecode that will differ from what is defined in the prelude. As a result, I think it is better to bake in the prelude in the compiler so that we can always guarantee that we have the same version of the library file and of the functions, of the symbols within it, rather than risking having a discrepancy. The downside being, of course, that any change to the prelude must be accompanied with a new release of the compiler. But the upside is we are going to be able to do some fun template Haskell nonsense, and I'm looking forward to it. A small other thing, outside of the stream, I did a tiny bit of work, not on the project, so it counts. It's not code for this project I have written outside of the project, but I wrote a very trivial input graph visualizer for Haskell projects. And my goal was to try to see, is there a proper topological sort of the folders of my project? And clearly, pipeline, which is where everything takes place, depends on the export stages, internal stuff, and representations. That makes sense. However, we can see here that batteries and representations have imports from one another, and internal and representations have imports from one to the other, which means that maybe some of the stuff in batteries and internal should not be in there. Maybe those two folders should be rethought to remove this kind of problems. So that's something that we might want to take into account, especially since I was planning to add the prelude into the batteries, which will probably make this graph a lot worse. So something to keep in mind. Let's get started. So we will want to go in the batteries folder, and we already have a prelude file that contains nothing, okay? So let's define what functions we want for our prelude for now. So I think the two things we will want are going to be a read int, which will perform some side effect and read from the standard input and read an int and return an int as a result. And the body of this function for the purpose of this will just be return read int. Same thing of like, this is technically correct, but completely wrong in terms of behavior. Like the typing is correct, the behavior is wrong. But calling this function, the goal of it will be to add another int on the stack that has been read from the standard input. And we will probably want write int, which will be a very basic, takes an int as an argument and prints it to the standard output. And this, of course, will be defined differently. So for now, I'm going to leave this body empty. This is going to be our two first built-in functions. So now what we will want to do, I'm going to get prelude again, which means it's the third prelude file in this folder. That's fine. What I will want to have here is to define I will want to define what the prelude interface is. So when we've done the analysis and we've output something that can be used to do the analysis of other modules. And so this will be something like this, prelude interface. And ideally, I'd like this to be known at compile time. I want to load a file from the disk at compile time and run my compiler at compile time to get this at compile time. How can we do this? And the solution is, of course, and this is where it gets tricky, template Haskell. So this will be the result of running some kind of template Haskell like thing in which we will do some stuff in the monad that is used at compilation time. I don't know how I want to format this. Maybe something like that. So what will we want to do here? I think I'm gonna. There's a few places where we already use a library. There is, for instance, in export HTML, we use embed file relative. And I think the problem is that this gives me a byte string and I don't exactly want a byte string. So I think I'm going to do something different instead. I think I'm just going to write Haskell code directly, but I'm going to look at the way that one is implemented. This one is what I wanted. The only thing is, I think if I look at the code of embed file relative, this is embed file, of course, which is adding a dependent file. Okay. and just doing a read file of run IO, which is some template Haskell nonsense. Let's go to template Haskell th syntax. I think this is where most of the stuff we're gonna need is. I think, or is it just in th itself? I think is here that there is the quasi monad here. This is where there is the add dependent file. There we go. And I think there is a function for this. Okay, perfect. So what we can do is, oh wait, is there even make relative to project? There we go. Okay. So here, if I go back to this, this thing, being a template Haskell splice, will be evaluated at compile time, which means this runs when the compiler compiles my compiler. So what we're going to want to do here is first, we are going to want to get the proper file path, which will be the result of getting this make relative to project. And of course, this is going to be, if I look at the HTML, it contains the lib, so it's going to be lib, lang, and so on. There we go. So that will give me the actual proper path to this file at compilation time. Here we can get the content by doing a run IO, I think it is. Run IO, there we go. Of read the file at the file path. Here, I don't care about this being partial and maybe failing, because if this fails, it's a compilation error for us, and that's perfectly fine. I will need, however, import data text IO qualified as T. And I will need, of course, import, and it is language Haskell th. Now we're gonna want to do the thing that the embed library does, which is to, how is it called again? Add dependent file. There we go. Add dependent file of the file path. So now at compile time, this registers this file as being a dependency of the project, which means if this changes, then this module has to change, is changed and has to be recompiled. Now we have the source of our prelude file, and we have because we have read from the file path. What we can do with it now is compile it. So we can do parsing and analysis like we would with any other module. So we can go back to what we do in compile, but it's going to be a lot simpler because we don't need to run simplify. We don't need to do any of this. The only thing we do, parse module, where are you, is parse the module. Source, so that's file path and source. And this is going to give us the resulting, if I go back to parsing, this gives us a module, but in a diagnosis monad. So we will need to probably do some kind of run diagnosis of do, and this will give us diagnostics and result, if I remember correctly. In fact, this is going to be a let because I'm not going to run this on top of my IO monad. So this is just a normal value. There we go. So parse module that gives us our module if everything worked. And now we can do the analysis. I go back here. How do we do the analysis of a given thing? This is going to be analyze module with all of those things. Hello. Now, the big thing is none of those are actually required because since this is the prelude we're compiling, there is no need. Hello. It's been a while. How have you been? Now, the only thing is we need to decide what the module name is, and the module name will be a hard-coded, I think prelude is just what we want, and a module name is a non-empty list of identifiers, so this is gonna be pure prelude. Now, this will give us our interface, which is what we want to return. However, there is going to be one issue there. So we run the diagnosis and we get either diagnostics, which is warning errors, something went wrong here, and maybe our result. So first, we are going to want to report all of those diagnostics as errors in our template Haskell monad. I don't remember how that works, but let's have a look. Actually, this might be in there because I am interested in the quote, which is a quasi. There is a report error, I think. There we go. That just takes a string. Okay. But this does not abort the computation. Fail does. Okay. But still, I think we want to report all of those as errors, and then this result is a maybe, so it will tell us whether the thing succeeded or not. So what we can do is, for each of the diagnostics, we get something like this. For now, we don't have proper rendering of diagnostics. One day we will have that. So for now, this is just going to be a show of the thing, which is not great, but that's better than nothing. And now at the end of this, we need to return. Basically, what we want to do is a case of our result of, and if it's nothing, then we can fail, could not compile prelude, which again will be a compilation error of our compiler, not of the hello, how are ya? This will be a compilation error of our compiler, not of the source that is given to us, because again, this is all template Haskell, therefore this is all evaluated at compile time. Now, here is where we might run into issues. In the case where this succeeded, we get the prelude interface. And I would like to just do that, right? But the problem is, what this must evaluate to is not an arbitrary value at compile time. It must evaluate to something that can be to code, basically, that can be used for the next phase of compilation. Specifically, this needs to be a Haskell expression. So it needs to be something that is a constructor with a name applied to other things, or specifically me an apply of a constructor on an argument, and so on. So it must be decomposed. This value must be decomposed into basic Haskell components so that it can be used to generate some code. This is extremely complicated to do, and we're not going to do it, because instead, we can do this and basically say, generate the proper expression for this thing for the next compiler stage. However, if I remember correctly, this requires some type classes on the types that we don't have. So now let's try to make this compile. How on earth is this broken? Because it's not something we have touched. I don't think I have touched this file. Oh, I removed some old file that were there. Weird. Okay. So here we're only missing the very classic data hash map strict qualified as M. Now, not in scope. Make relative to project. Is it in? Is it in this one? We saw it there, right? Make. I don't know enough about Lisp to be able to tell you if it's like quote unquote. Oops, sorry. Let me just fix this. It is in syntax. That's my issue. There we go. So basically, there is a very. Oh, you're absolutely correct. That is because I have Redshift was enabled. I think if I disable it, it should become a bit whiter. I have this thing that shifts the color of the screen to be more amber at night, and I forgot to deactivate for the stream. But for template Haskell, the idea, I could look at the wiki for it. Wiki template Haskell. Because there is... The Haskell wiki is not great. Yeah. There's a specific thing I have in mind. Maybe it's documented here. Oh, no, it's in the GHC manual. But the gist of it is basically that now every stage of compilation, like there is different tutorial. There was a very good one. Give me one sec. Yeah, this graph is what I have in mind. But basically, there's this notion of level and compiler stages. And basically, what template Haskell allows you is to run Haskell code at compilation time, including code of the files that you're currently compiling. Like, for instance, if you have a module A that depends on a module B, A can do some Haskell at compile time that depends on B because B has already been compiled. So you can do that kind of stuff. And here, what I'm doing is I'm basically saying this evaluates at compile time to an expression. So whatever this Haskell code runs, like including doing IO, this does like whatever this Haskell code does at compilation time, but must evaluate to something that can be used by the next stage of compilation. In this case, an expression. There's a few other things you can do with it, such as evaluating things that evaluate to declarations. A thing you've seen me use quite a lot throughout this project. If I go back to, and yes, this syntax is part of template Haskell. If I go back to, do I have a make lens? I have like make lenses here, which is a thing that declares lenses for a given type. Like I have this module type here, make lenses, declares the lenses. That is template Haskell stuff that runs at compile time to generate new definitions in the scope. And yeah, the idea is a quote like this transforms the thing that you need. I was mentioning that like the in a splice that it must have the type expression or pattern or type depending on the thing you're generating. The quote takes something that is a Haskell thing and generates the proper expression or type or pattern or something that allows you to avoid having to declare it yourself. There was a good template Haskell tutorial. Which one was it again? That I like. I think this one I liked. Yeah, I think this one was a very complete and very well written explanation of template Haskell. Let me put it in the chat. So now let's finish fixing this. Run diagnosis we don't have in scope, so we need to, sure thing. We need to bring into scope, that is internal and diagnosis. There we go. And parse module, that is, oh, that's gonna make my graph of dependencies absolutely ugly. Because that is stages analysis and stages parsing that need to be in scope. Okay, so I don't need to do a pure there because it is already monadic. So there we go, that should be it. And now I should be getting no instance for lift interface. And that is a tiny bit annoying, but that's fixable. That just means that if I look here, there should be a lift class in this thing somewhere. Lift, there we go. That comes from, okay, so th syntax as well. And the only thing that I'm afraid of is, do we have to write the lift instances manually, or is there a way to, language derive lift? There we go. Is that included in GHC 2021? Because we are currently running with GHC 2021 enabled. I don't think I have derive. No, I don't have it. I don't have derive lift enabled by default, but let's see. Derive lift is already enabled by the fact that we have GHC 2021. So I should be able to just do a derive lift. Yeah, deriving lift. Perfect. So now I just need to go and fix every single thing that depends on interface to have a deriving lift. This is fine. So interface here, this needs a deriving lift. And lift, it's going to be so commonplace that I think I'm going to go even all the way to my prelude. And I am going to add to the things exported here. Is it language? Haskell th syntax, I think it is. And I'm just gonna include lift in there. Which means now every module has lift by default. I don't have to add a bunch of imports everywhere. But now that means all of those things are gonna need lift as well. And I hope that I don't run into a situation where like sec or hashmap doesn't have lift, because if it doesn't, this is gonna be very annoying. It will mean having to write the lift instance manually. Let me check hashmap actually. Oh, I don't see lift in there. I don't see lift in there. No. Okay, that's gonna be annoying. Well, before I move any further then, let's have a look at what lift requires. Because maybe lift is not that complicated. Okay, well let's see. Let's see how good the compiler is at deriving lift. Will it be enough to just put it on interface, or oh, this is gonna recompile everything because I've touched the prelude. There we go. Okay. So yeah, it looks like we're gonna need to do a bunch of lift everywhere. Some of it might need to be manual, which is gonna be very annoying, but that's how it is. So first, with location. So location will need lift, and it's strings and ints, so it should be fine. With location will need lift. It's a location and an A, so as long as A is lift, it should be fine. Now we get into the weeds. Common function info. So that is representation past, in fact, representations common. Let's do the common function info. This will need a deriving lift. And so many things are gonna need it. So function type and block are gonna need it. Which means function argtype is gonna need a lift as well. Path info is gonna need it. Common block is with location statement, so statement needs it. Which means at this point, I'm kind of tempted to do a do I still need generic here? I don't think I do. I think I had this only because I had a hashable based on this. I don't think we need it anymore. Identifier. Deriving lift. That's a long enough list. I might want to make it vertical at some point for readability. Here, expression type. What is an expression type? Oh. Oh, this is annoying. Okay. So this is going to be, I'm going to have to duplicate, rather than doing this, I'm going to have to duplicate, where are my show constraints? There we go. I'm going to have to do lift constraints, which is basically this type, which is a type family, for the thing that contains it to be lift, then all of those type families must be lift, which means here I can't do that, and I need to do this. Same here. Same here. It's been a while since we've seen those types. It's been a while since we've had to touch the AST. Months, in fact. So this one's going to be the same. We are going to need, because if you remember, all of those types are parameterized by a parameter p, which is not a type, but a phase, which tells us which version of the AST this is, passed, resolved, verified, validated, I think, is the one we use. And we associate different type using type families so that we can decide what the AST looks like based on the phase of the compiler. Okay. But the downside of it is it's a tiny bit more verbose since we have to do those deriving instances and we have a few more issues like this, where since we have non-injective type families, the compiler gets slightly confused. Okay. Don't forget to remove those deriving lifts when I replace with the proper deriving instance. There we go. If hash maps don't have, I'll be tempted to add a lift instance for them in my prelude as an orphan instance, because that would be a lot easier. But I do like this idea of this very compiler that we're compiling, we are running at compile time as well. Okay, expression type, where were you again? Oh, this one is wrong as well. Oh, in let info. Use a standalone deriving instance, but that's what I'm already using. Ah, here I have another of those deriving lifts that needs to go away. Okay. Likewise, this goes away. Let's see. Is that gonna be everything? Import. That's not too complicated, because import is a much easier type. That is this. So here I should be able to just do deriving lift. I probably will need... why do I have a deriving instance here? I don't think I need that anymore. I think this can be back to a deriving show and lift. Well, actually, in the interface, we don't have the module, I think. So I don't need lift here. Okay, so we're just missing now lift on a few places. If I go back to... Wait, I removed the lift on the module, so... Okay, so import type here needs lift. I will definitely need it for declarations, but I think the error we had was because of having it on module. Role, so that's in the resolved version of the AST. A role here in which, in fact, we are going to be able to remove built-in function, so that's good. lift name. Aha. Name is gonna need a lift, which means base name is gonna need a lift. Okay. Let's go look at a validated definition. That's the wrong validated. I want to look at representation AST validated. I'm tempted at some point to remove the plural from the folder names, but that's gonna be a bigger change. So, oh, that's ugly. So definition in here requires, where are you definition? Here, this requires lift, which means this is probably gonna require lift, and this is gonna be a lift again. And I might as well just put lift on all of them. It doesn't hurt. And in fact, is likely to be required. Let's see. I probably need more here. Type node. Oh yeah, I didn't do node yet. Okay, range expression, even though it's not used yet. And the L value expression need a lift as well. And now the only thing is the type node here. Enum info, interesting. Is that something from this module? Or is enum info coming from somewhere else? From common, it seems. Yeah, I suppose there's no difference between enums at any stage of the compilation. Yep, so this one can just get a lift here. Okay, is that enough? Nope, it is not. Struct type info. Oh yeah, that's correct. We forgot that one. Let's see. Okay. We're moving. We're moving. The module we're trying to compile is, I think, the last one. So, and we still have to compile the parser in the meantime. I really want to move the parser to megaparsec at some point, just for compilation speed, for supporting the syntax I wanted to support in the first place, for many reasons. Okay, let's see. That is an error, I suppose. What do we have? Yes, I suppose this does indeed mask the pi float. So let's call it instead prelude interface. Let's be explicit in our naming. Which is already the name here, I suppose. Interface. There we go. Naming is hard. And now, hopefully, there we go. So now this compiles, which means that at compile time, this piece of code run. And at compile time, we run our own code to generate the interface for the module that was at compile time read from this file. I'm happy this standard Haskell code worked basically on the compiled, which means ran on the first try basically, except we had to do a lot of changes to lift. But now let's observe the result of our labor. Oh, it has to recompile everything. Okay, so now I'm in GHCI. I should have access to Prelude interface. There we go, which is an interface. And if I do a show on it, this was compiled, this was obtained at compile time. And we do see that we have no dependencies, but this exports write int and read int. And there's the definitions in them and there and everything. So there we go. I'm happy it worked that fast, let's be honest. So now we do have, bundled with the compiler, the interface for the prelude. Let's actually commit this on its own, because it's already a pretty big change. Because we've added lift to the prelude. Actually, I'm going to just commit that on its own first. And those are the comments we added last time to, so I'm just going to commit those. So this is just all of the lifts, basically. Let's commit all of them. That I'm going to commit on its own separately. And this one is adding the prelude. I'm not going to add that yet. So first, project at this point, the scope is all of it. Add lift instance to interface. Then let's do this cleanup. Because this wasn't even compiled. This was just dead code that was left pre-refactor of last summer. So that's out of the way. It messed up with my the thing I was talking about earlier, that dependency, this import graph dependency generation, because it was trying to parse files that are not part of the project. Next, we will probably want to add. No, I want to remove that, and I need to add this. There we go. So now we can. What do we do next? I think next we move back to resolved and we remove the idea of a built-in function, because that's no longer required. The built-in types are required for like int and stuff, because those cannot be declared in terms of anything else. So those need to exist for the type resolution to work. But built-in functions no longer exist. Those are now normal functions that happen to have been imported from Prelude. So let's remove this and let's see what breaks. I think not much. Because since we didn't have anything for them yet, there should be no part of the code that was actually handling built-in functions. Which means I probably had like a unimplemented thing for the lowering into AR. And I think otherwise the rest of the code should work just the same. Which is good if that's the case. Okay. What do we do here? Yeah, unimplemented. Perfect. I am delighted to see you go away. Unimplemented. I am delighted to see you go away. Okay, that was it. That was about it. That's always good. So now we've removed this. What do we need to do? We have an interface that contains functions that the rest of the code can call. If we go back to our compile here, there we go. So basically that means we need to fake. We don't want the prelude to be included in the build plan because it's already built enough for us. What that means is we need to add a fake import to the prelude here. And when we run compile here, yeah, the prelude needs to be added to the things we are aware of. Okay. So let's start with that one. Let me just check whether this is urgent. It is not. This is just the fact that the tests are broken in the CI, which I already knew. So let's start with the monad, because again, this is our context that we carry around. The modules we have parsed, the interfaces we have extracted, the object, and so on. So here we will want to, when we run compile, start with a compile context that is not all just empty, but in fact contains in the interfaces, which is the second thing here, actually I think I'm gonna change this to make it a lot more explicit rather than this long list of MMT, which is very unreadable. Which for now was just MMTs, right? Yep. Because those are all hash maps. Yeah. Okay, so here the difference is this is gonna be a singleton of, and I guess I could have not this prelude, this prelude. I could have prelude module name, which is gonna be a module name, and which is gonna be this thing we've been using. Which means here I can say this is a singleton hash map from the prelude module name to the prelude interface. So now other modules should be able to use that interface for their imports. So next, it means the compile here, when we compile a given module, we need to modify the module info. Oops, sorry, let me just check something. This will need to be modified to contain. So here, this is going to be add prelude to the module info. So we're going to need to define add prelude. Which is going to be a function that will take our module and return a new version of the module in which the prelude has been added. And add the prelude for a given module that has those fields. Oh, in fact, I can use the lens for this. Because I do have lenses for this, right? Yeah. So it should be just a matter of over the mod imports lens, I do a modification by using this operator in prefix position. And what I put here on the left of this is gonna be something that just contains with location import. So I'm gonna need to make a fake location there, I suppose. Ah, that's annoying. Huh. I do initial location I have for a file path. But do I still have the file path at this point of this particular module? Like, I wouldn't need the file path here. Do I have that when I compile the module? I don't. I don't. Hmm. Okay, so I need to change something. So I suppose my build plan needs to give me my build plan needs to persist the file name so that I know what the file name was, so that I can create a fake location for where that fake import I'm adding was located. Yeah. I'm trying to think of like, can I make a fake location that just doesn't have anything? But I think this is basically what it is. A fake location that has anything is that. So I just need to make, okay. So that means create build plan, which is here. It gives me a sequence of module name and module. And I think instead it's going to give me a sequence of module name, file path, and module. Which means wherever I create that tuple at the end, module name, parsed module, there we go. I will need the source path. I think that should be all of it that we need, which means here we do the build plan. We traverse uncurry. Is there an uncurry 3 actually? Google to the rescue. Uncurry 3. There is. But not in data tuple extra, which is part of extra. Yes. Okay. Because extra is something I have already as a dependency. Perfect. Uncurry 3. There we go. So now compile module is called on module name file path module. That's the source file. And here that means when I am adding the prelude, I can give the source file as an argument, which means that here I have the source file as an argument, and the import I am adding is a with location and a fake location, which is the initial location for that source file. And the value inside is an import. What is an import? If we go back to past, This is an exhaustive import of the module name. So this is prelude module name exhaustive. Okay. So we're faking the fact that there is at position 0 in the file an import of the prelude. Because I think I could also change my analysis to be here when we resolve the dependencies and everything, which is in analysis resolve. Here, I could change to, instead of just looking at the imports, where is that done again? Create in scope. Here, there we go. Here is where I do the thing where I go through each imported module and I create a hash map and everything. I could cheat here and initialize this with the prelude, but I find it cleaner to let this thing operate normally and just inject a fake input to the prelude at the top level. Because this makes the code, this removes exceptions and weird edge cases from the code. This code just like sees a import of the prelude and imports everything. Okay, so now add prelude to import, that's done. We don't have the cache yet. That's a problem. But now the problem we have is that if we try to compile something that uses the functions from the prelude, we'll get a link error because some of the symbols will not be found. In fact, let's compile this and let's try this. Let's play with this assumption and see what happens. So I need, of course, here to import batteries prelude. Module name, that's not something that's in scope. I probably just need name. Aha. That's okay. That's a limitation of template Haskell, which makes a lot of sense, which is this thing is executed at compile time. That means that it cannot depend at compile time from expressions in the same module. It needs to be able to run the code, and therefore it needs to be code from other modules. Therefore, this use of prelude module name here doesn't work. Downside is I now have this defined in two places, but as long they are very close, hopefully I should be able to not make a mistake there. Here, this is in prelude module name. This is... Oh, I haven't added... Interesting. I thought I had. There we go. Okay, now this compiles, which is good. So if we go back to our test file with the Fibonacci function, now here, if I should be able to do this, read int here, this should compile. Well, this should do most of the compilation because this is fine. This is, and I can do in fact write int here because those functions now exist. They are part of the prelude. So this should be allowed. However, this should get a link error because those functions are not, those functions don't have a definitions in the objects and therefore will not be found. Let's try. Okay, error definition not found. That is considered an internal compiler error. Okay. At validation context. Ooh, so that fails a lot earlier than I thought. Why is that? Retrieve input definition. Aha. Retrieve input definition. Because I am looking at definitions. So that means, I think, that we need to go back to our compile monad. Because here, when we add an interface, we don't just modify this interface's thing. We change in fact, I'm tempted to do something different. I am tempted to go back to all of my MMTs. All 1, 2, 3, 4, 5, 6 of them. And instead, what I do is set up prelude followed by the action, which means whatever this action in the monad is given to me, I start by doing a setup prelude, and setup prelude is an action in my monad, which happens to be add interface of the prelude module name and the prelude interface. And that way I will do all of the operations on those hash maps correctly without having to duplicate this code. Okay, let's see if now we go past validation and do end up with a linker error like I expect. Not implemented yet. Huh. Interesting, in generation, okay. At line 127. Oh, is that? It's this one right there, right? Yep, it's this one. And that is because we have not done code generation for functions that do not return a value. Well, I guess there's no time like the present. Let's do that. At some point, this will have to be changed with the way I want to handle references in the language. Rather than returning just a register or nothing, functions will be actually returning a list of registers. The ones that have been modified, the references that need to be given back to the caller, and the possible return value, if any. So instead of having a maybe case and a nothing case, and like just case and nothing, I'll have instead a list case, and I think I'll be able to simplify this code. The big issue with this, however, is that I cannot use this append operation, which is very, very annoying because it is convenient. Because if I go back to append operation, which is here in the generation monad, append operation, there we go. So that's what we do. So I'm gonna have to duplicate this because we don't have a target. Or maybe I changed this then. And instead, I make this a list of register, which are my registers that are the target. Which means what I have to do then is for each of them, for each for each register in the targets. The only question is, will this have to be reversed, or will I give them in the proper stack order? Since for now this is irrelevant, I think it's fine. It just means that now every call to go here or to append instruction will be broken. Append operation. Okay, so it's just go in this function. That's fine. Which means I can probably do a go target into go target. And that means, does that mean that now this is just always the same thing? I don't need to do a special case for it. And this is now a maybe to list of the target. I keep thinking that there's a way to make a maybe to list. There's an easier way. Is it just an asum? Foldable alternative. No, it's not. It's incorrect. Because I feel like maybe a to a list of a. Because this is to list, maybe to list for sure. I don't know why it feels like there is an easier one. It's not a fold. Doesn't matter. Maybe to list is clear enough. So now, hopefully, that should be what was missing for the generation. Let's see. It was not. Targets plural. Okay, this compiles. Let's run again. And now, okay. Ooh. That is a panic, but it is now in the linking phase, which is good. But that means, however, that we don't handle link errors very gracefully. We could try to do better than that. So linking at line 37. Yeah, here we assume that the address will be found. Yeah, we do some lazy stuff shenanigans. The problem here is that if we try to do something that changes the monadic operation based on whether the value was found or not, then the whole lazy operation crumbles on its own, because suddenly the whether we do go do the register depends on whether we found the value, and time travel has not been invented yet. That's not possible. So that means we are going to have to be a bit smarter than this. We might have to rewrite we might have to rewrite the linker to be done in two phases. Because what we do basically at this in this thing is we visit all of the functions of the program, and for every entrance that we find, we assign a unique address in the program, basically. To say, so that when we do things like this, we can say that this is entrance 1, this is entrance 2, 3, 4, 5, 6, 7, and 8, basically. That's a gist. That's the gist of it. Well, there's more, but you get the idea. And so we traverse the program, and every entrance gets assigned a unique integer. And every I mean, yes, Stardust is, but that's basically what I'm doing at the moment. Because what I'm doing at the moment is whenever I encounter a push of an address, something that puts an address on the stack, I look up that address from the hash map from name to address, even if it has not been encountered yet. The way that works is I'm doing basically both traversals at the same time. And if we look at linking monad, if we look at run linker here, if you look at this, I do a run state, which is like, okay, we go through the monadic state thing, which is the thing where I keep my hash map from my list of address of int. So where I accumulate all of the addresses I have assigned, and I run reader by creating a hash map from the final state, which is the result of the action. So here, the result of the action, which gives me the final state, is used to run the reader. I do this kind of circular logic like TARDIS does in a sense to be able to do in one run. So when I do a read of an address, it might not have been written yet, but thanks to laziness, as long as at some point in the future it is written, then we will be able to tie the knots and be able to make it work. Which means I am doing some kind of time travel already at the moment where I might read an address before it's been written. Now, the problem is laziness can only go so far. And the problem is now, if I try to make a decision based on this, then it needs to be evaluated. If it needs to be evaluated because we're trying to see was it found or not, then we need to evaluate this thing, which depends, and then the whole thing crumbles. So I might have to break this down and not use something that traverses the functions only once. I might have to break it down into something that traverses once to collect the addresses and traverses a second time to then assign them. Which, not the end of the world. Let's do that now. Does my linking monad... It's not... I think I will want to make it so that it is on top of another monad, and I'm gonna remove the linker info. It's just gonna be that, and it's just gonna be a hash map address int. Okay, and run linker will now be something that give me something in the underlying monad. And now I no longer need to keep the state, so because I no longer do any time traveling shenanigans. So this is now purely a run state t of the action with the initial state. So my beautiful time traveling shenanigan goes away. That's fine. Which means this run linker is now inside the monad, which means I can do things such as reporting errors because I have a monad diagnosis constraint here. So this is going to be traverse, assign, collect addresses of all the functions. and then a second traversal of all of them, which is replace addresses of the functions using the hash map we have collected. So now this becomes collect. Well, this might actually be replace addresses. And we'll duplicate it. Well, it doesn't matter. To make collect addresses in the first place, which will be we'll be able to simplify. Okay. So that hasn't changed. Function entrance. Where's that again? Use current. Okay. Why did I use the function entrance for? Oh, because I am on the function and I'm iterating here on the instructions, of course. So here, whenever I find an entrance is when I need to do this thing. But for now, I am leaving the entrance unmodified because this is leaving them unchanged, I think. This is this is doing nothing, basically. This is purely... Since this is purely modifying the state, I don't even need the result. I don't need the pure function here. Ah, it's annoying. That's not true. I'm gonna need some of them, those operations I'm gonna need to do. One sec. I need to think. I think I'm gonna need to change the functions. Ah, I cannot. I cannot return the thing. Okay, that's fine. That's annoying. So this traverse does nothing, but this one does the replacement. So okay, so I think that's correct. Here we do nothing, so entrance count goes away. Entrance count is not changed. And in the registry, we do in fact insert name address. So that hasn't changed. In every other case, we don't care what the instruction was. We only care about the entrance. So in every other case, we do nothing. The total count and all of that is for replace. So after we've done this traversal, we have assigned a unique integer for each name. Okay. Here is where we're gonna need monad diagnosis M. And now we can do the replace addresses, which is similar to what we had before, where whenever we enter this, we do the entrance count thing. But now we don't care about the current. The current was only used for this phase, to the point that I'm almost tempted to separate it into two different monads just to make it more explicit. Oh well. But now, whenever we find a push address of a name, this is where we do the lookup of the target and we replace it with a push int, because we now have the address. So, but here, now that we can make a decision based on this, we can do a lookup of the name. On nothing m of this, we can do a report error and figure out what kind of diagnosis we want here. It's going to be this kind of diagnosis. And we need a new diagnosis message. Error symbol not found with, what are those? Address. And what is an address? Name and label. And I think the name is what I care about. So I think name will be because the only way for a symbol to be not found is if a function doesn't exist and that the name is enough to uniquely identify it. So I think that's enough. So it means here, back to our linking, that we can do here symbol not found with the first part of the name, which is now a lot cleaner. Now, when we find an entrance, we still need to do the entrance count thing, but current registry doesn't have to exist anymore, and we can do the replacement. Now, all of those have to remain the same. That's annoying because we convert from one type to another. So even though they are the same thing, we still have to do a case for all of them. And now that should be all. Okay, let's try to compile this. Yes, we don't have linker info anymore, so there's no need to generate lenses for it. This is a empty hash map and no longer a list. And here I do a run state, but I only need the eval state. I don't need to keep track of the resulting state at the end. And I need a monad m constraint here. And this is a 4 underscore because we discard the result. Of course, this is no longer a view of the addresses. This is now a uses of the registry. Oh, function entrance is gone. That's probably... God damn it. Hello, how are you? This is annoying. I was keeping track of the function entrance by looking at the context. I guess I could still do this thing. I could reuse what I was doing here. So I reset current, basically. Which is set to 0 at first. Oh, first addressable entrance. I think that's ugly. Let me think of something better than that. Because I do have the information. Because here, when I find an entrance, I could instead keep track of the first entrance I have found. Because here in my result, I have a list. Yeah, maybe I remove the entrance count thing. Yeah, maybe I remove the entrance count thing. Which means this goes away, which means this goes away, which means this goes away. And instead here, I have my result, and I can extract the total count and the function entrance from it. And this is going to be just going through the list of instructions and keeping only the entrance. How do we do that in an elegant way? Because total count is basically a length, a sequence length of a sequence filter is entrance of the result. So that's the easy part. So that's the trivial case. I can even save one line. Okay. And now the only thing we need to do is find the first entrance. And let's have a look at data sequence. Find. Come on. There's no find? No. Is it that the basic find is on foldables? Nah, no, that would make no sense. Maybe on traversables? Nah. Sequential searches take well span L. Maybe LM index? I find index. Okay. But I don't want to find the index. I want to find the element. Huh. Because find, the good old find, the prelude one, it is on a foldable. Huh. So I can just use that find instead. Okay. So this will be, and the function entrance will be a do of find is entrance, I guess. It's here. It's just a condition on the thing, yeah, I suppose. So find is entrance of the result that gives me the first entrance on nothing reports internal compiler error. We managed to have a function that didn't have an entrance. That's never supposed to happen. Something went completely wrong. linking replace addresses. Not found. There we go. That gives us, therefore, that's not even monadic at all, because that's just I guess I could use this in the maybe monad. No. So that's the entrance, and actually I need that to be monadic because that's an entrance, therefore that's annoying. Because now I need to do a case on it. Okay, let's do a separate function for this. Find first entrance will be a function that, given some kind of monad diagnosis M, let me go back here to have more space, takes a sequence of instruction resolved and gives me, in that monad is able to handle errors, gives me, in fact, in link M, gives me the int of the first entrance. Okay. So first we obtain let's do a from maybe entrance not found of something in the maybe monad, which is first the instruction which is obtained by doing this find is entrance result. Is the indentation correct here? I'm surprised it's correct. Let's do that instead. And let's do a case of it of entrance whatever, this is the name actually. Wait, am I doing all this for nothing? Can't I just... I know what the shape of the entrance is, right? It's always going to be an address which is name of the function and labeled 0. Could I avoid doing this? It means hard coding my assumption about the shape of an address, but this would be probably so much better. Okay, I don't have something for first address? That's annoying. Because I know it's going to be name, that I know I have a name of the function, I have access to it. I think. I can easily have access to it. And it's going to be a label, and the label comes from the AR. And I don't have here the thing where I say, okay, no, let's continue with that. Why I don't want to hard code assumptions about the shape of a label. Okay. So here, if I do find an entrance at a given address, then I can return this address. If I find anything else, nothing. So this pure is just let's make it explicit. That's the address. Now, if we do a from maybe on this result, entrance not found will be the error case, and that will be entrance not found, and that's going to be this report internal compiler error. There we go. Now, we are in the case where we have the address, and we can do the same thing we do for all of the replaces, which is do a lookup. And on nothing here, I am going to use instead, I'm going to use the entrance not found again. That is an internal compiler error. This should never happen. This is not a diagnostic that we need to surface to the user. This should always succeed. If it doesn't, something went wrong. And now that gives us the actual int. So now we can rewrite this as function entrance is find first entrance of the result. Okay, let's try to compile this, and now we should be able to collect linking errors without crashing. LC entrance count equals 0. We don't need that anymore. Find is entrance. Why can't you find that? Oh, because is entrance here is this small helper function. Just gonna make it here. This is a function that takes an instruction with whatever phase and returns a boolean. This is the result, which I'm going to call the instructions. What time is it? Okay, not too late yet. Oh, those are resolved. Ah, God damn it. This is fine. It just means I need to give the base instructions, not the result. And therefore, those are unresolved. That's the whole point of resolving them, is I remove the name that's no longer required. Something here assumes I'm still calling find first entrance on the result. I need to call it on the instructions. Wait, why did I change? Here it is result. It's here that I needed to change it. There we go. Reward ice not in scope. This is from here. Okay. Now, hopefully that's everything. Defined but not used. Yes. When I collect the addresses, I don't use that at all. Proper error handling is really annoying. Okay. So this is now... I'm just gonna do that. Okay, now this compiles. Let's go back to our test. Now we should get, instead of getting a crash, we should get a proper diagnostic of symbol not found. Crossing fingers. Diagnostic, error, symbol not found. We try to link read int, and we didn't find it. Now, I want to make one change. I want to collect as many of those as possible, which means if we go back to diagnosis, how does that work again? I know there's a try logic in there. Yeah, try gives me a maybe. And then I'll have to ensure this at the end. Okay. So that means if all of those, if replace addresses can fail, then I need to do this. Oh, yes, I was doing this everywhere in the analysis. This is going to be a try nested of replace addresses, and this is going to be the ensure nested. There we go, because I'm going to compose the thing. So there's going to be an ensure nested of traverse, and now I should collect all of the errors rather than stopping on the first one, and yet still failing if errors happened. And now, oh no, we still only get an error for read int. Interesting. That's interesting. I was expecting to get 2 errors there. Oh, oh, of course. We get 1 error per function. And the problem is here that those might. So I want to recover from this, basically. So perhaps what I should do is do a try nested there as well. That way I will collect all errors for this. And now, okay, now I do get linker error, read int, and write int are missing. Let's have a quick look at what our IR and stuff looks like with the new changes. If I go back to that's the wrong file. I want debug here. I have main HTML. So our function here. So write int, read int were correctly resolved to be pointing to the prelude version. So that's correct. Nothing else has changed. And we have only the dot file, so I need to quickly run a dot. There we go. If I look at the PNG result, now we have a call to read it int, a call to read int here before calling the Fibo function with register 0. And then we have a prelude write int with register 1, and everything else remains the same. Okay. Perfect. So now we do have support for built-in functions. As far as compiling goes, linking is still broken. So now we need to start writing, and that's going to be tricky. We are going to need to basically build the bytecode manually for those functions so that it can be added to the object of our compiler and can be linked against. Now, the big question is, how do we name this? I am half tempted to put it in here since we already have all of the interface there. My only issue with this is that I feel like this is backend specific. And what I mean by this is whenever we do exporting of our IR to the LLVM IR, then we will need to provide an alternative definition of those functions that isn't just Pete bytecode. And as a result, tying their definition that is used for the compilation thing to what they look like from a code generation perspective bothers me a tiny bit. I'm half tempted to create a backend folder for like start making opening the possibility of multiple backends. But I think I'll do that whenever I get to actually making other backends. So for now, I think I'm gonna put it here, even though I don't like this a lot. Because in the same way, code generation and everything is linked to Pete for so far. So I'll have to let me just do a thing real quick. Okay, so yeah, I think for now, since my implementation is really tied to Pete at the moment, I think I'm just gonna add it here, but with the idea that at some later point, I will move this out of the way to instead being in a specific dedicated backend for when we want to support other things, such as the LLVMAR. Okay, so this means we will need to export a prelude object, which will be, if we look at our compile monad, an object. What is an object? That's in bytecode, I believe. An object is a hash map from name to instruction buffer. Okay. And our prelude object will not be something we need to like use template Haskell to compile at compile time. This is just going to be a basic hash map of the different functions. And again, this is why I think we want to have this in the same part of the code as this, because we are tying the list of the functions defined here to their implementation here. So we're going to have, read int, which will be a read int bytecode, and write int, which is going to be write int bytecode. And those are just instruction buffers. And in fact, I think I'm going to add another language extension to this file. Oops. I'm going to add overloaded list so that I can just use list notation for things that can be created from a list, such as a sequence or a hash map. And now is where we decide what the bytecode for this function is. And it will therefore need an entrance. So this is going to be an entrance at first. This is where the function starts. And it will need parameters which are its name, what is a name again? This is a base name and no parameters. Okay, do I have a pattern for this? I don't. And the module name and identifier. Okay. So this is, that's a non-empty list, but it has a from list instance. So I should be able to say that this is a name with prelude read int and no type arguments, because it doesn't have type arguments. And its entrance is the label 00. Okay. So that's the entrance to our function. What do we do then? I think we probably just int. That's the base Pete instruction to read an int. I need to check if this pushes a value or if this overrides whatever is on top. And pushes it to the stack. However, If no input is waiting on stdin, this is an error and the command is ignored. Oh god. That means we need to figure out a way to detect that the stack hasn't changed. Oh god. Oh, this is going to be tricky. This is going to be tricky. Because here, the only thing I need to do is I need to check that the stack hasn't changed. I think I'm going to assume that read int only accepts positive integers. Let's have a look at what npit does. Let's go look at just an example. Is there a... There we go. Let's look at the code. Oh god, that's all C code. Is there a list of the symbols in this file? Yeah. Get cell. Okay, so that's perfect. So if I go back to here, read of an int is 4 changes in hue and 2 darker. This overall case is on the hue change, and we said 4. So this should be it. Read the value from stdin as either a number or character. So this should be in of a number. God, this indenting is very weird. Aha, this is a F scan F with this format. Does this... optionally signed. Oh no. So what I'm trying to figure out is, how do I detect that read failed? How do I detect that a read failed? Because if this can give me any arbitrary int, or this could be something that, in some cases, this will just show a prompt, and like this is type a prompt to the thing. How do we detect the end of the stream, basically? To detect the end of a stream, we need a value that cannot exist, basically. I am tempted to decide that I don't care about this for now, since apparently it's an error even to just try. Now the command is ignored. For the sake of making progress this evening, let's ignore this conundrum. And this is gonna be then, we have done an in int, so we have pushed. Yeah, that's gonna do that thing. I'm just gonna handle the success case. So we've pushed an int to the stack, which means our stack is now the return address on top of the value, which means we need to swap them, which means we need to do a push int to push int one roll, so that the return address of the function is now above the return value, and we return. Next, with this big caveat, I need to look at out pops the value of the stack, so I need to be careful. So write int bytecode will have on top of the stack a value which is, it's fine. It's not a reference. It will be copied to be called to the function. Therefore, I can just do a out int, which pops the int from the stack, and then I return with my return address on top of the stack. So with that done, and with this big caveat that this is broken, we can't detect the end of the, which is extremely annoying. We can go back to compile. What do we do when we have compiled a module? We do objects inserted here. Perfect. So now we can do the same thing inside the pipeline monad here. When we set up the prelude, we add the interface, and we can modify the object to add prelude module name. And we can inject the prelude object, or whatever we called it. Prelude object, there we go. So that now when we link things, we should have access to the proper definition for those. We need bytecode in scope. Aha, yes, of course. And scope label. Huh. Oh, label comes from the IR. So we need even more things here. Bytecode return. Okay, so we are gonna need to as BC as IR to make it clear which one we mean. Well, in fact, I only need the label from the IR, so maybe I just import the label there and I avoid the conflicts because I only really care about the bytecode. No instance is string name. Oh, those are names. Okay, so read int name is this thing, which means that removes some duplication, which is always good. Write int name is this thing. So that's here is an entrance for the read int name. This is an entrance for the write int name. And those keys are read int name and write int name. Okay. No instance for isList base name. Oh yes, I need to be very explicit about the fact that this is a base name. What is in the name again? Oh, it's module name identifier, of course. So this is a base name where the module name is just that, and the identifier is that. Okay. Illegal term level use. Wait. What do you mean? That's a type. What do you mean? Oh, you're correct. Thank you. Good catch. I imported the type, but not the constructor. That's correct. Thank you. And there we go. And now let's have a look at what happens if I do this. That compiled. So now let's close all of those stuff. Let's open our new program. Oh, I didn't do the pruning of functions that are not used. Oh no, there isn't. Hehe. This is not. I no longer have additional unused functions in this. One of those is read int, the other is write int. So we have, this must be our main. I should add a debug view for the bytecode, because not being able to read the bytecode is a bit annoying, but I think this is our main. And this is probably just, yeah, this is just print int, write int, and this is read int. There's more instructions there, because we do the roll 2, 1 roll there before returning. Okay. Well, no time like the present. Whew. What would be? I could draw something there, but that's a good point. As long as I don't write anything above, like, that blocks the pathway, I could give a name to each function. The problem is, like, trying to then bundle ASCII art in this thing. But I could, I suppose, yeah. So I want to do a trace image, and I want to run program.png. It asks me for a number, let's say 5, and it prints 8. And I think that's correct. I think that's the correct Fibonacci value. Now, if we try 12, it runs for a bit longer and we get 233. Is that correct? Twelve is 144. Huh. Oh, but because I am one off by 1, it seems. Well, according to the AI result, which may be wrong. Okay, so 5 should be 5, and I have 8, and I typed 12. It is, so I am off by 1. Okay. But that works. That is pretty nice. So what is wrong here? Or is it because this uses 0 and 1? Okay. So I should fix this by saying if greater than 0 then? Wait. Oh, it says f0 equals 0. Oh, okay. So I could do it as greater than 1, but here return 0. Yeah, yes, you're correct. Else, if x greater than 0, return 1. Else, return 0. Pass error. I am missing the closing bracket here. Programming is hard. Oh no, something is wrong. Huh. Did we encounter a bug in the compiler? It's really struggling on a basic if then else thing? What's happening? It's not that complicated. Yeah, that's probably an infinite loop somewhere. I probably have a bug in the handling of ifs then? Hmm. Let's see. Since I do have export AST, export IR, we can see whether... What time is it? Yeah. If I keep the else, maybe I could actually put it... If I try this, if I put this if within... That compiles. And if I give it 11... Oh, it seems it's broken. It's not even asking me for something. So something is wrong. Okay, so even this is broken. Well, that's what tests are for. Wait, we don't have those. Okay, let's debug. So now we do have a program that's been compiled with this. This is going to be a good opportunity to, I think, add exporting the bytecode. Because we can go here and go back here and look at that. This was passed correctly at least. This x is the same as everything. Nothing has changed here. Okay. But let's look at the IR. I think the IR is going to be interesting because I think it's the IR that's broken. So that means I just need to run dot again. Oh, there you go. So here, what do? We have more branches. The branch true hasn't changed. We subtract 1 to x, we call Fibonacci recursively. We subtract 2 from x, we call Fibonacci recursively. We add the results and we return the register. That hasn't changed. Now here, we have the block 3. Its argument is name 11, and this is the x argument that was given to the function, okay? So if x is not greater than 1, we have x in register 11. We compare greater than register 11, register 12. So we are comparing is x greater than 0. If true, we move to block 5. If false, we move to block 6. If true, we return 1. If false, we return 0. So the IR is correct. So now we need to figure out why the bytecode is wrong. That's interesting. Okay, so we need to add probably some kind of debugging thing. I want to do one more change. I want to go back to the previous version, the else if here, because that, I don't understand how this makes an infinite loop, and I suspect it is 35. If I run this, and goes into an infinite loop. If the bug is in the code generation, those two phases will have run before. Yep, there we go. So I can look at the IR that's been generated for this. And it's exactly the same. Okay. If I do a cat of debug main.dot, that was again changed right now. Just checking for block L5 return 1. Yeah, it's still the same. So that means this is still the same, and that is correct. Oh no, it is incorrect. Aha. Here it is missing the argument. We are calling I3 with no argument. That explains the infinite loop. Since the IR is incorrect, our stack reordering, yeah, the arguments are missing here. Well, no, those blocks don't require arguments. That's correct, because we don't use any value from any previous thing. But this block, however, is missing an argument. This block is missing the register 11 that is there. So we have a bug here in the AR, which explains the infinite loop, because we're trying to do some reordering of the stack that never finishes. So we can start by solving this one, I think. I might actually first commit things. What have we changed? We've changed a lot of things. We rewrote the linking first. I'm gonna put that separately. What did we change here? Oh yeah, yeah. Okay, so the linking we rewrote. To report errors to the user rather than crashing. That's better. Then we removed built-in function, and the only place that changed was this one. Okay. So st remove built-in function. Perfect. Next, we've added, it's going to be last, I think. In the generation, code generation, we've added handle functions with arbitrary number of return registers. It's a bit long of a commit message, that's fine. And then all of this is inject prelude into compilation monad. Okay. Next, we want to debug a few things. First, we want to go back to the IR generation to see why, when we do the if else thing, we do not get an argument here properly. That's interesting. So this would be in stages, IR, or well, lowering. So this is probably here in an if statement. We process if. So what do? We create a register. It does use the right register in block L3. So here, basically what is missing is the argument register 11. That is, in fact, 11 is not declared anything, but it's used here. But 12 is local and set to 0. 13 is the result of doing the comparison between 11 and 12. And then 13 is used for the branch. And it's then every block here uses only 14, 15 that they declare locally. So the only one that's missing is 11 being given as an argument here, which it was in the previous version. So I suspect that here my else block here works, but my else if does not. Is that because I don't seal block first? Okay, let's see. I get the register for the expression of the if. So this puts all the instructions for the expression itself and gives me the register that will contain the result. I create a label, which is the block, the if block, the else block. Okay. If there is an else, then we create a label. Otherwise, we just reuse the resume label. Okay, which is where we go after the if. And the block ends up with a branch, which is the if block label, the else block label, and the register. That makes sense. And the else could be the resume label if there was no else. Then we seal the block of the if block label. We start the block. Why do we seal it first? Because we know all of its parents, yes. And we process block of the if body. We need to always end in a... Okay, that makes sense. Okay, but I think here's the problem. When we find an else if, I do a start block, but I don't... I think I should be sealing this one in both cases. Yeah, I don't see why I wouldn't do that. Because that should be the same thing, basically. This should be... Does process block do anything that process if doesn't do? Where are you, process block? No, it just immediately jumps to processing this. Yeah, I think there's no reason for this seal block to be missing. I think that's the issue. Okay. So now, if we try this again, one thing I should be more careful with, I am getting close to a point where now that we have a pipeline, I should be adding tests for those things so that I can then check afterwards that they are fixed. Okay, so here now running this finished, I run dot again, and now I have sealed the block properly. I do have the register 11 coming from this. We have the exact same code if I do an else and an if then, or an else if. Okay, so that's one problem fixed. However, this program, this version of it, is still incorrect. There's something wrong with it. We get an infinite loop. Could it be a problem of the address being wrong? And we jump to the wrong address? So let's try to run it again. And wait for a tiny bit. That should be enough. And let's have a look at the trace. that was just generated. Ah, come on. So we enter the start, which pushes the address of main. Main is this function here. We go here indeed. We push the address of something. And it seems we never go anywhere from there. So maybe it's a problem of the linker. We linked the wrong address, possibly. Because we just go back to the loop there. And it seems we never re-enter anything else. So we have a bug where we are probably pushing the wrong address there. We are pushing 14, 16, and then we are doing a roll, I think. 14, 16. 14 is the return address, 16 is the function we're calling. Oops. Is that the correct one? It's not. Our start calls main by pushing, is that a 15? Or a 13? Okay. It does go there. But push 14 would be the return address that's correct. And 16 should be the address of therefore 13, 14, 15. It should be correct. Oh, is it just that doing the trace is so slow that maybe actually it works? What if I just don't do the trace? Nope. Okay. Okay, so now let's add more debug stuff. First, lowering fix missing. It is extremely nice writing a compiler in Haskell. Fix missing seal block in else if case. I mean, when I did write my own brainfuck compiler, I did end up writing my own brainfuck debugger. I don't want to write a Piètre interpreter though, because that is the realm of nightmares, because having to deal with how to segment an image into blocks of pixels, that's complicated, and I don't want to do that. But maybe one day. Okay, but for now, what I want to do is I want to go back to our pipeline options, and we are going to add a new flag, which is going to be export bytecode. Yes, so what I'm compiling is Rust-like code, like this. So that looks basically kind of like Rust, and that's the goal. In fact, I think if I enable Rust mode on this, yeah, Emacs is happy. That's just Rust code. And it compiles it to Piètre, a image-based programming language, which is esoteric. The whole goal of the project is not to be a serious compiler. No one is going to use this in production, right? But it's just because it is fun and serves as a good introduction to compilers and Haskell projects, I think. And now it seems I have some bytecode generation issues, so let's go back to my options. I'm going to add an export bytecode option, which means, what's your language actually? And I need a new option here, export bytecode. I mean, true, but also, come on, who's going to use Piètre, right? I mean, some people using it, maybe for like the advent of code or something, but real production use? Nah. This is going to be export bytecode. I'm tempted to rename them with like lowercase ASTIR bytecode folder in which to export the bytecode. So that's one more option. Now we accept that option in main. And that means that back in our compile pipeline, we need here. Okay, we have the objects. We don't have a compilation cache yet. We don't do incremental compilation yet. But here is where we can do when just export AST. So it's going to be export object of the module name and the object, I suppose. Okay, so now export of the object. Well, export bytecode. Let's be consistent with how we named our option. And in fact, I see an error right there. This is not the correct option. This would be export bytecode. I can't type, I'm sorry. And here, then, we do the same thing. We get the folder of the thing, we write to file, and this is going to be render bytecode, which means we're going to need to import export bytecode, I suppose. And we get to write yet another renderer. If we look at the IR1, just call that's perfect. So let's say now bytecode. And its function will be something like that. I have an object. Come on. And I want some text. And I will need the bytecode in scope for sure. In fact, I probably won't even need the IR. I will need the label, probably. And even then, that's not even sure. Okay. So what do we do here? I'll definitely go have a look afterwards. So this will be render bytecode. Come on. Which will be the only thing exported from this module, which means everything else will be internal details. And this is going to be something that for each of the things will give me. So what is a good way to render this? I guess this will be some kind of concatenating a bunch of. So there's going to be a T unlines, where T is text, of concatenating a bunch of lists of lines obtained by doing a map with key or doing a map of unquery render function of two lists of the object. Okay. So that means our render function will be taking a function as defined by the bytecode. And in this case, do I want the... No, it's pre-linking. So this is going to be... It's not going to be a function because it is an instruction unresolved. So this is an instruction buffer. And this is also going to take the name, which is the key in the hash map. And the key in the hash map for an object is a name. So that's name, instruction buffer, create some text. Now, what do we do? This is going to be some kind of list of lines. Well, this is going to be a list of lines, in fact. I guess I could do a concat map here instead. So I get a list, and I then do an unlines. And here, I guess my first line is going to be just rendering. So it's going to be a render name of the name at the beginning as the first line of indenting, I suppose. I probably want to do an intersperse, something like that, to add an empty line between the things. And here I map an indentation after doing a render instruction of the buffer. So that's our thing. So how do we render a name? Typo there, and a typo there. I'm going to copy what I've done for the IR so far. Not that one. I do have a render name somewhere in there. Yep. I'm going to copy this. I should probably at some point deduplicate those functions, but so far that's not a, since it's debugging stuff, I don't really care that much, but it would be still good to deduplicate them. Okay. And I'm probably gonna want to add, it's fine, since it's indented, it's fine. And I just need, therefore, render instruction, which is gonna be taking an instruction unresolve, because we haven't done the linking yet. And we return some text. Render instruction is gonna be a big case of every possible instruction. So let's do that. That's our big list of cases. Push int of x. Can I just use a show on this? I think I can. I think the two only ones on which I don't want to use a show is push address and entrance, because those ones have like this is gonna be a both of those are gonna be addresses. So I think those I don't want to do a show, but any of the others, I think I'm perfectly happy with a show. So this one, however, I think I will want to do a push address with render address of this thing. And here I will want to do an entrance with render address of this thing, and rendering an address is going to be something that takes an address and returns some text there again, and rendering an address is going to be given a name and label, which is a label with two values x, y. I did indeed need the label from the IR, is going to be render name of the name plus something like that. Let's try to compile that. And let's see what's wrong. Intersperse. So if I go back to here, each block has like a unique number that uniquely identifies it. And when I translate that into code, basically each block is a series of instructions that ends up in a jump. The label that I use for the address in my bytecode is the first number is the number of the block, basically. So this would be the address FIBO built-in int 0, and this would be the address name FIBO of int, and the x would be 2 because this is block 2. However, in some cases in the process of generating the bytecode, I have to create more entrances. I have to create new blocks, as it were, that are not present in the AR. For instance, an example of this would be if I go back to generation. Here's the exponentiation code. There's no exponentiation operation in Piètre, so it is made by doing a bunch of things, including having a new entrance there and having a jump back to a condition, because I'm basically doing a loop manually there that was not present in the base code. Since I need to create new entrances, I use the y number as a way to differentiate them. So if there is no new entrances, all of them will be just be like, this will be the entrance, this name 00. This will be this, the entrance here will be this name 20. This will be the entrance 30. And if any of them needs to introduce new entrances and new jump points, new go-to destinations that will be picked up by the linker, they use the sub-index of the y value of the label for this, so that I can just add them without having to then like move all of the values of the other things. So that's why I have two values in my label. Since I don't do any kind of like weird, since I don't do any exponent or anything like this in this program, we should probably not see, we will probably not see any kind of non-zero y value in the debugging today. Okay, so what was wrong here? Probably because it is intercalate that I want. I never remember which one is which. Intercalate is the one if I have a list of A as an argument and a list of A. Yes, that's intercalate that I want. And intersperse is a list of A. Okay. Concat map uncurry render function. Thank you. Thank you for the follow. So here I have an object, which is a hash map from, as we've said, if I go back to the bytecode, an object is a hash map name instruction buffer. So if I uncurry, if I toList, I get a list of name, tuple name. Yes, there will not be any LLMUs on this stream ever. As long as I live and breathe, there will not be any slop on this channel. Oh, it's the return type that's wrong. This expects a list of text. In fact, oh, of course, yes. Since now I have done a concat map, I have a list of text. So what I need here is an intersperse, in fact. And just, oh wait, no, since I already did do a concat map. So maybe I need to do a normal map. So I get a list of text. I intercalate this thing, and then I do the concat. Yeah, no, I'm a AI hater. I will never touch those, and I will try to find a job that doesn't require me using them because I refuse. Okay, so what's wrong here? So now I have a list of text. I am doing an intercalate, which is the one that takes a list of the thing, a list of the thing. So it needs a list of text, and I'm giving it a list of this. Huh. Let me just type this for a second. Foo is a list of text, and it's that. And here I do a unlines concat intercalate. What is happening? What is that wrong? It's just a matter of overloaded strings? That would be weird. So it's a list of text, which is what intercalate. Am I using the wrong intercalate? No, it's used unqualified. It's the one from the prelude. So if I list a list of text here as a second argument. Oh, wait. No, yeah, here. I am giving the wrong thing. Still, I'm getting the wrong thing here. Interesting. Oh, is this because GHC is confused and doesn't realize this is an empty text? That's probably what it is. And not a list, in fact. Hmm. Okay, let does text give me data text? Where are you? Do you have an empty? Yes. Okay. So if I use here empty, will you be happy? Aha. In the first argument of intercalate. So I think I have the wrong intercalate. Which one is that? Do I just want to use... Oh, wait. No, intercalate is on lists, and I have list of lists. Weird. Because this intercalate is not the one I want. Hmm. What happens if I say that this is text? Will this fix the problem? Or will this just shift it? It's a good point. I could try this just to make sure I have the correct one. In the second argument... Oh, it's the inference that's wrong because of this. Okay. So I intercalate text into... So I think something is wrong in there that made the type inference go wrong here. So this gives me a list of text. I intercalate... Oh, but intercalate into a list of A, so the concat is no longer required. That's what's happening. And now this should be fine. And we move... There we go. So now I should be able to rewrite this 0.3 in all its glorious non-unnamed fashion as it was. Because I just got lost in my complicated chain of operation there. So that should work, and I should probably even be able to do this afterwards. Yep. Because I had forgotten that intercalate would do the concatenation. There we go. Okay, so now this is wrong because I do a map instead of a. I just need to do a to list of the buffer if I want to return a list at the end. No instance for is string because I'm forgetting the concatenation operation here. Correct. I'm not using text builder for this. Okay, that should be everything we need. Which means, nope, it is not. So here, export bytecode. Did I expected IR? Oh, it's probably my export bytecode, not render bytecode that's wrong. Yep, here, that's the one that's wrong. That expects an object and doesn't need a file path. It does need a file path. Yes, that's the folder. So that's the object. And here, this is gonna be this is gonna be some text file, I suppose. And we render the bytecode, which is the object. There we go. An object is not in scope, and it comes from bytecode. I'm just gonna get that and nothing else from it, just in case I don't want to introduce more name conflicts in this file. Oh, I'm also gonna quickly run a thing. It's the thing I worked on before this. Yeah, I still have the big thing between batteries and representations and batteries and stage. I'm trying to have like the folders of my project have like be topologically sorted, but clearly like pipeline depends on export, batteries, stages, and internal. That makes sense. And representations as well. It depends on all of the others. So they're clearly the one at the root of my topological sort. But I have a few edges that are broken, and I've introduced a new one between batteries and stage this evening. Okay, I'll have to fix that later. Probably by splitting the built-in types away from batteries and putting that in the analysis, I think. Okay, it's compiled, which means now we can go back here and I can run this again. And now I will also export bytecode into debug. And I've renamed those options. They are now lowercase, export AST, export IR. Okay, so now it compiles. So now we can go back and we can check. Oh, I need to quickly rerun dot just to be sure. Okay, so now I refresh this. Huh, wait, didn't we? Oh, no, we left this. Shouldn't I actually? Oh, no, it is the else if. It's fine. It is good. And it's fine. Okay, it's still the else if. The one that was broken that we fixed. Okay, so this is all still good. This is all passed correctly. No change here. Here, no change that I can see. We do pass the registers correctly here. 11 is given correctly as an argument here. That looks all good to me. So now, oops, the one thing I want to have a look at, I can close this actually, I don't care about it. This main PNG is the old one. Can probably close a bunch of stuff. Oh, that's the documentation. I might want to keep that for a moment. Okay, and let's have a look at that's unreadable. But we can still have a look at what happens here. Okay, we do have some y values. Oh, because of the functions, of course. So our main now is the entrance, which is main 0, 0. We push an address, which is the address of main 0, 1. Is this big enough? Let me zoom it. Then we push the address of read int at 0, 0, which will be the linker. Basically, what the linker does is it translates all of this into numbers. So it translates all of those push ints into push addresses into push ints. Then we return so that we go through the whole loop of going to the address. We're going to this address, and our return address is this one. When we return, here's the entrance 0, 1, which is the return address after doing the function read int. We push address 0, 2. Why do we have a 0, 2? Because we are going to be calling another function. Yes, of course. We push to one roll so that the value on top of the stack, which is the result of the read int, is above the return address, which is main 0, 2. Okay. We call our Fibonacci function. Well, we push the address and we return. Then when we come back, here's the entrance for 0.2 of our main, which is the return address of the call to the Fibonacci function. We push a 3. We push 2, push 1, push roll so that we put the address below the value on top of the stack, which is now the argument to this function write int 0, 0. And at the return, we come back here from this function call and we return. So that looks correct to me, which suggests that the problem is the linker? Huh. That's interesting. Because if that is correct, we should enter read int, and we should therefore be prompted by npete for a number. But the fact that we never go there means that the linker is broken. That's interesting. Okay. So let's do... Could it be a problem of reordering of functions between... Could it be a problem of reordering of functions between... They have the same key in the hash map, so the ordering should be the same. I don't think hash maps guarantee the order. Maybe that's the problem. Hello, how are you? I think the problem might be that. It might be an ordering problem. Let's see. Let's add some more debugging options, and let's print what it looks like after the linking phase, when we have associated an address to all of those, so we can see where this goes, basically. So let's do the whole dance again. We go back to options. Export binary. Without a typo, that's even better. We add this as an option, so we need to add it to our option parser. Binary, export binary, folder in which to export the binary. Okay, that's all good. Next, we can go to the compile here, which is our big thing, compile module. When we're done compiling the binary, this is the link of all the things. We can do the same thing as this. When just view export binary, export. I'm tempted to do an export bytecode because it's the same thing. And that just means I need to change my export bytecode because what is the return value of the linker? It is a binary, and what is a binary? It's probably defined in the bytecode as well. No, not this one, the other one. Huh, where is it defined? It's clearly defined somewhere. Do we have data? It's a data. Oh, and it has its own folder. Aha, so it's not a matter of ordering because we do store the functions as a sequence. Okay. Okay. So that means that if we go back to our compile here, I can't just reuse export bytecode. Let's create an export binary that gets the binary, and it has no module name because this is after we're done linking and there's no longer a module name to be considered. Export binary doesn't take a module name. It takes a binary, which will need to be in scope. Binary, no, binary. And this is the same to the point that I should probably deduplicate this. Let's do it quickly. Well, except it's not in this case. I can still, okay. Given a module name, this should give me a file path. And that is just this, basically. Well, given module name and folder, I suppose. This will be this thing. It's the folder concatenated with intercalate underscore of, yeah, that looks good. And I just need the extension, I suppose. So this is gonna be a string, which is gonna be the extension here. Okay. That means here for bytecode, I can replace here file path by generate debug path of the module name, the folder, and .txt. Remove that. And I'm probably just gonna do it with parentheses to be consistent. For the IR, I can do the same thing. This becomes but dot here. This goes away. This goes away, and this becomes, oops. Shit, what was the AST again? HTML? It was. Here I can do the same thing. There we go. Okay, so that's a bit better. For a binary, I suppose I could fake it by hard coding the module name. Generate debug path. The module name will be of my own invention. It's just gonna be main, I suppose. I want a name that cannot be confused with, I guess main is fine. And I think I'm gonna need to do a pure main here. And folder. Actually, you're right. Debug is a lot better. Well, I think I like main just because that is the name of the module where we're compiling always. The name of the module that we compile is gonna be main. Oh, I guess I could actually no, I could get a proper module name. Well, no, I mean the module name of the file that we get is always assumed to be main. So main is technically correct. I think I'm okay with main, but I'm just gonna add a debug thing. So folder here doesn't change, and the extension is gonna become .debug or .linked.txt. There we go. And this, I'm tempted to try to see if I can do a render bytecode. But I don't think so. What is in a binary? It's mostly main address and functions. No, I'm gonna need a special function for this. So render binary of the binary. I'm gonna put it in the same thing here because this is basically the same stuff. But that's after linking and before linking, basically. So we get a binary, which comes from representation binary. It bothers me to have the plural on this folder. That was a bad decision. I'll have to fix this at some point. And this is exported out of this module, render binary. There we go. And I think the only thing we need, I guess I could put the main address. I think it's not not useful. So this is gonna be instead of this thing, because there's gonna be only one function. There's gonna be only one big thing of instructions, right? Oh no, it's a sequence. I'm wrong. I'm completely wrong. Okay. Let me do this and put the binary here on top so I can see what I'm doing. Good enough. So here I will get a binary of some sorts. And I will probably want to, without a typo, unlines something, and the first line will probably be something about the rendering the main address. So header at the beginning of something which will be the intercalate this, that's correct, of something else, and the something else is probably going to be a to list of fmap render linked function. I don't have a name for that function anymore. So maybe instead I'm gonna do this as a map. I'm gonna do this as a zip with, and this is gonna be a list. I need to be careful this time with infinite lists. And zip with render linked function. Of two lists of the function. So this zip with on a list gives me a new list, which is applying a function to those two things, index and function. I intercalate, if that gives me a list of text, I intercalate an empty text in between to add empty lines. I add the header at the beginning, which in fact, I'm going to do this so that the header can be multi-lines, and then I unlines. Okay. And what is going to be my header? My header is going to be, oh, in fact, no, I'm just going to do this intercalate here before the header. There we go. And the header is just going to be main show of the B main address. Okay, so now I need another thing here, which is going to be render linked function, which is going to be the exact same, except here it takes an int, which is the index. So this is purely a show of the index before I put all of the instructions. And now the big thing is I will want to render instruction exactly. I want to do this for any type here, but that means that the type here needs to be able to be rendered regardless. And that means I need some kind of local type class, I suppose. Let's do that. So this is going to be and naming thing suddenly debug render. Yay, there we go. Where debug render is a thing that takes the thing and returns a text. There we go. And there's going to be only three instances. Debug render of unit will give me nothing. Debug render of an address is going to call render address. And debug render of void is interesting because it is absurd. With that, I can say, as long as, if I go back to bytecode here, how are they called? Push address. Okay, so now I just need to say, as long as there is a debug render for the push address of the phase P, and there is a debug render for the entrance address of same said phase, then I can write a function that takes an instruction of that phase and returns some text by calling in those two cases here debug render. I am saying basically, as long as whatever the types of those things, regardless of the depending on the phase in which we are, can be rendered with debug render, then this function can exist, and yeah, that should be fine. Okay. And I will want just to, for clarity, to go back here. It's push address. Okay, what's wrong? Oh, yes, of course. This takes a function instead. And the kind, oh, I'm going to have to specify as IR, as BC, as BI, I suppose, because there's going to be more than one function in scope now, because the function compile is not the same thing as the function pre-compiled. Yep, so this one, when I do a linked function, that's this one. I guess for the IR, I don't care, so maybe instead I just do label here. Aha, yes, here this functions need to be, so I don't need the thing here. This function here is parameterized by the type of the thing it takes as an argument. And as we've seen in binary, this is this, a sequence of instruction resolved for which I don't have a type alias for once. What time is it? Not too late yet. Okay. in the first argument of dollar, namely header of, okay. Oh, yes, of course. This is not a function I'm applying on this thing. Now, okay. Aha, those are, so I need to do a list here. Or I guess it would be probably better to have it as the header being a list here so I can change later on if I want to add more things. Oh, actually, I would be tempted. I could do a thing where I count the entrances and I print the number with them so I can check what I'm doing. Since it's probably a problem of linking. Might be worth it. I might try to do that if I can't debug easily what's wrong. Buffer is not what it is. Because here this is a function. And what I rendered this as is purely to list of the function instructions. Ooh, okay, what's wrong? Could not deduce phase types. Huh. Do I need? Yeah, I suppose I need to add this constraint for it to make sense. So that's phase types of P there. Almost. What's wrong? So here export binary is missing something. Oh, because I'm still saying I take the module name here, which is wrong. There we go. Okay, that compiles. We can now add to our long list of export binary into the debug folder as well. That worked. So now let's compare. I mean, linked. Yes, it does. Okay, so that's... Why is it labeled as loading? Interesting. So main is 13. Ha, okay. Yeah, I think I will want to... I will want to add indices to the entrance so that I can see what I'm doing. So that means I need to do some kind of either state monad or something like this. Which means maybe all of this render instruction is going to be a bit different. Yeah, okay. So actually, I don't need to do that. This is unresolved, and that's just render address. And I can remove all of that nonsense. And all of this goes away. Okay, so here for function, this is the render unresolved. Here, this is the resolved. And the big difference is now Wait. Where did I break? I changed something there. Where's the zip with? Oh, it's here. Okay, so here this needs to change. Because now this is going to be obtained by... This is going to be some kind of flip eval state. My starting state is 0. And the action I will do is going to be a traverse with uncurry of render linked function on 2 lists, which is 0 and 2 list of the B function. Okay, so now this is a traverse because now this is monadic. And I eval state to get the value out. This is the output of this thing. And now I can just say output here. Okay, so that means render linked function is now something that outputs something in a monad of my choosing. And in this case, it happens to be in a state monad in which we carry an int around. And this is going to be very similar. Okay, noisy outside, but the noise cancelling removes it. Perfect. This is going to be traverse render instruction on the instructions. That gives me a list of 2 lists on the thing here. That gives me a quit output again, and the result of this function will be pure of show index and map this on the output. Okay, which means now render resolve instruction is also a monadic thing, which is a state int text, and now this purely returns, in this case, pure. And it's in those cases that this becomes interesting. Push address here, push address doesn't exist anymore. I don't have to handle it. So the only interesting case is here. That's the entrance with the address. I don't care about the address because it is just a unit at this point, because we are in the compiled version of the code. What I care about is getting current address, which is my get from my state. I modify my underlying state to do +1. And then I return, in this case, entrance between, after, before show of the current address. Okay, let's try that. A render instruction no longer exists. This is now render unresolved instruction. Wait, no, this one is resolved. Okay. To list f instructions is not one thing, it is the function application into space. Okay, we got some interesting things. Uncurry render linked function. Oh, of course. This is on the zip of this. Because I zip this with the list, I get a list of tuple. I traverse, there we go. And here, it is in fact resolved. Okay, that links. Let's see. So I try again. And I refresh this, and now the entrances are labeled with a value. which means I can go look entrance 13, and that is wrong. Wait, I might be wrong here, because I think my linker does not start at 0. Because I think my linker remembers that the two first should be... Is that a problem with the start function, in fact? Okay. So first, let's fix that. I run my eval state somewhere here with 0, and I cannot use that. I should be using instead... I don't want to use that directly, but I can at least look at it. The first addressable entrance is 3. Yes, the start function is inserted after. And it calls to main. Okay, so that means here I need to start at 3, and I probably want to not hardcode this. To do not hardcode this 3. Okay. So main is 13. We go look entrance 13. And it's this function here. We push int 14, which is the return address of this thing, and we push int 17, and then we return. Entrance 17 is this one. That's the one that reads an int from the command line. Push 2, push 1 roll to put the return address. We return to entrance 14, which is there. Push int 15, which is our return address, to here. 2, 1 roll, push int 3. Wait. Push int 3. So that's the address where we're going to. We're going to the address of 3 with the int that we had, and then we return to 15 afterwards, and 3 is Fibonacci. Okay. That looks correct to me. So what is happening? Why then, if I open program.png, it's unreadable. Let's open it in this. Make sure that we have the correct version. Oh, it could be if I have a bug in the number of addresses. Now, this is 1 here, that's correct. That's 2 here, that's correct. But this one, how many pixels is that? Well, I mean, I designed this, right? So I designed how this functions. 3, 4, 5, 6, 7, 8, 9. So this claims that there's 9 entrances in there. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's correct. Okay. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Yeah, I suppose I could just try running npit again. And it just gets lost. So let's run it with trace. Trace. Okay, I think my stack is growing a bit too much. Okay, so let's also generate the image. Actually, let's tlog. Oh, Okay, that should be enough. Now, let's see what we have when we look at the trace. We seem to be just looping forever between the same functions. We never actually enter them. So we do start correctly at main. We push 2, which is the return address here. We push 13, which we have seen is indeed the address of main. And then we go to main, which is this function. And here main pushes 14, pushes 16. That's consistent with what we have seen. Pushes. Oh, this says push int 17. And here this is a push int 16. Before a push int 1. Oh, okay. So I think the problem is instead of pushing 17, like we should, we are pushing 16 and then we are pushing 1. Oh, but no, that makes sense. That makes sense. I know what's broken. So the thing that I know what's broken. A push instruction in Piètre pushes an int on the stack which matches the size of the block of pixels that came before. Since it's the color transition that encodes the instruction, color from this color to this color is a push, and the push will result in pushing 16 because it is the size of this. I didn't want to have blocks that are millions of pixels big if I want to push a 1 million value on the stack. So I decompose pushes into basically in base 16 basically. So what's happening here is I should be pushing 16 and 1 and multiply by 16 and 1 and then do a +1. But here somehow something went wrong and the bytecode that was generated did not do the 17 correctly. And we never encountered this before because I never had to do a push of a constant greater than 16 before. Okay, so that's the problem. So now we can go back to assembly. Because here is where I have expand instruction. And when I encounter a push int, this is where I try to decompose it into. Yep, I mean, a big reason why the last weeks I've been pushing on like having the whole pipeline of the compiler is I want to be able to write tests because I have 0 tests except the manual tests so far, and it is really starting to hurt me. Same time, until last week, we just didn't have the ability to run any program yet. So 2 weeks ago, rather, but still. Okay, so here. Yeah. Yeah, there we go. That's the problem. Well. So this is saying if it's less than 16, just push that value directly. If it's less than 32, less or equal to 32, then push in 16 and push the thing and then add them. But I had forgotten the add. Another thing I could think about is I should probably test actually pushing bigger values. I'll do that in a second. But first, that means, in theory, that with this 3 character change, 5, counting the comma and the space, I should be at a point that now we run our program. Oh, I didn't copy it. There you go. it asks me for the value, so it did do the jump correctly. Let's say I had the Fibonacci thing. Let's say now, let's say 16. It's going to take a long time. Let's say take 15 for now. It says 610, and that is correct. Now, that is pretty big. Let's commit that first. It is close to midnight. I'm not going to be doing a lot more, but there's a few more things I want to do. So first, yeah, it was faster than I was expecting. I'm happy about this. So first, export bytecode is neat, and options, and here in compile, I have export bytecode, and I have the two new exports, and I have the cleanup here, and I think that's it. So I can make that into a commit on its own with the commit here. Okay. So that's that, and then we have this fix. Okay, so that's pretty big. There's a thing I wanted to try as well. Let's try, because I'm expecting it to be slow if I do 19 is 4,000 something. It's not that slow, but I was tempted to try to see how we perform if I rewrite it as a loop. Because this is... Because I don't have 4 loops yet. I don't have 4 loops yet. But I could do something like if x is 0, return 0. If x equals 1, return 1. And then otherwise I can do something like let x equal 0, well, not x, let's call it n instead. I have it as a generic function because I was testing the instantiation of generic functions, but we don't need that at the moment, so I can maybe do that instead. So it's no longer a generic function. I have x equals 0, y equals 1, and it'd be something like while n minus equal 2, while n greater than 0, n minus equal 1. Let z equals, let's do it in this way then. Nah. Previous is 0, current is 1, z, like let temp equals prev, well, no, current plus equals prev, and previous equals tmp, which is a swap basically. We don't have references yet, so we can do that. Return current. Something like that should be okay. There's probably an off by one error there somewhere. It feels so difficult to write code in a imperative language that I don't know how to do my Fibonacci here. So let's have a look at what's been generated. Okay. That looks good. Let's regenerate the dot of the IR. I want to have a look at the IR. Okay, that's more complex because now we start, if it is equal 0, 1, we go here, we return 0, okay? Otherwise, register 4, which is given the 0, which is our x, which is our n value. Oh, how did we name it? N. And here we check, is it equal to 1? If yes, we go there, we do a return of 1. And otherwise, we go to this block, giving it the value of x. Here, okay, that's all of the image. Here, what do? We receive as register 10 the value of... Oh, interesting, it's labeled as register 10. Interesting. We receive the value of x. We do 8, 0, 9, 1, 11, 2. We subtract from 10, which is our n, 11, which is 2. That gives us 12. And now we jump to the loop condition with 9, 12, and 8, which are renamed 17, 13, and 19. Those are now... This is 9, so that's the current. 12 is our n, and this is the previous. We compare 13, which is our n, with 0. If it's false, we are giving 17, which is our current, as an argument to this, and we return it. If it's true, then we continue doing the loop. We are given the current, 17, which is named 16 here. We are given the 19, which is the previous, which is 18 here. And we're given 13, which is our n, which is given 21 here. It's slightly reordered for some reason there. We add 16, 18, and we jump back. Oh, so the swap is optimized. The swap is optimized, TMP goes away. Nice. Because it's just a matter of how we call the thing here. We just add 16, 17 into 20, and we jump back with current being the addition of the two previous, n being the one passed there, and 16 being the old current. Yep, that looks good. Okay. This generates this, which is a bit big. Let's just run it. Ah, it's broken. Okay. I was so happy with the IR being correct that I was for a moment in the euphoria of the IR being correct, and no, this doesn't work. Okay. Well, let's trace this. I'm still happy about the IR being correct for the while loop. That's decent. And I wait, since I'm generating an image is a bit slow. Oh, no, it did reach... Oh, of course it did reach that, yeah, of course, yes. 5, and let's continue from there and see what happens. I'm not sure. Yeah, of course, it goes through the read int. That makes sense. Let's see, 300 steps. That's probably good enough. Let's have a look at the trace. So we go through main, we go through the read, and then we go through this, and we go so many times through it. Wait, why do we enter it many times? We should only be entering it once. It's a very different function now. Okay, let's debug the bytecode. Let's have a look at what we have generated for the bytecode. So now this is the entrance. We push, actually, it's going to be a bit. Let's try to have both on screen at the same time. There we go. So our entrance here is this entrance here. We push 0, we duplicate. We push 3 to roll. Duplicate, duplicate, push in 5, push in 3, roll. Huh. That is extremely complicated. Why would we push that 0 below the return address? Oh, not behind we are duplicating the 0. So we are duplicating a 0. So we have 0. We have n00. We roll it twice, so we have 00n. We duplicate n twice. We roll 3, so we have the 2 zeros on top of the 3 n's. Then we push roll. Okay. Oh god, that's going to be a nightmare to debug. This is basically setting up the stack to do the greater. Oops. And now we do the greater there. We add that. Do we have. Why do we do an add? This add is suspicious. When we compare things for equality, I do have an add here. Oh, there's no such thing as equality in Pete, of course. There's no such thing as equality in Pete, which means I have to do instead, is it both, is it neither greater nor lesser? Which I think this doesn't do properly. Because this does only one greater. Oh no, it does both. There we go. So if you have arg1, arg2, arg2, arg1, and this is the top of the stack, this is the bottom of the stack, I do a greater. So is arg2 greater than arg1? I push 3, push 1, roll. So I put this intermediary value behind the 2 remaining arg2, arg1. I do a greater. Is arg1 greater than arg2? And then I do an add, which is basically an or, and I do a not because. Yeah, that makes sense. Well, we know how to debug this. It's past midnight. I won't spend too long, but the obvious way to debug stuff is with printf debugging, right? So, time to do some printf debugging. And by which I mean I don't have strings yet, but I do have characters, so I can do that. And I can probably do a right. Well, new line is going to be with this already, so I don't need to do that. So that's going to be that. This function is good enough as it is, which means now I need to go back to prelude, and I need to add a new right character function that is here, that will be added to the hash map for the linker to see. And its bytecode will be fairly trivial because it is just the out character, and we return, and that's about it. And it's just acceptable. It's called right character name. There we go. So that's one new function added to the built-in functions. And now that means that I can go back to my test here, and I can do... Oh, n minus equal 1. Yeah, that's an infinite loop. I forgot to decrease n. There we go. I might not need the printf debugging. Although here I'm probably going to do a right character of a new line so that it looks better. When I said that I was struggling with imperative programming, yeah, I forgot to decrease my value here in my loop. That's my problem. Okay, so let's... Well, it's still good to have some printf debugging abilities nonetheless. Let's try to see... First, let's compile this, see if my new function works. It doesn't. So where did I fuck up here? The type is ambiguous. Fascinating. Oh, because I did not write the correct one here. There we go. Okay, that compiles. Now I have access to a new function, which is the right character. Now, oops, wrong one. We compile the thing. Aha, not implemented yet. Oh, that's probably assigning a character. I don't have generation. There we go. Yep, I didn't do assign character. This is just pushing the ORD value of the character literal. Compile that. Compiles. Regenerate the dot to go see the IR. Okay, that is parsed correctly. Ooh, that is very broken. Okay. Oh god, no. Oh god. I need to escape them in the export of the IR because here the \n is being interpreted by... Oh god, that's gross. Let me fix this. That would be if I go here and export. Yep, that is a classic for sure. That just means that whenever I do a node text, function, render instruction, I think render... I think the only place where this could happen is probably in here. I'll have to escape. If I do import data text qualified as t and I do a show of \n as a character, it gives it... Okay. So I probably... Wait, but it does? I do this already. So maybe I need to do a additional show here? That feels wrong. Let's try that. Let's see what happens. Aha. So let's have a look at the debug dot that's been written. Debug main dot dot. And if I go for the assign, there it is. Okay, so the text of this block contains, yeah, okay, contains a backcode here. That's wrong. Okay, so if I just do a regular show, which I was doing, then it doesn't put double quotes there in the middle that are wrong. Is there just in text? Data text is there. Oh, it's right there. And right there as well. Is there an escape thing? There isn't. Because now if I look at the dot file, oh, I didn't run the program again. There you go. Now it is indeed saying \n like this. Yeah, I think I just need to just escape the backslashes. That's just fine, I think. I do. I don't read as much. As a wise person once said, buying books and reading books are two different hobbies. Um, I have to confess that with the years passing, I still indulge the same amount in the buying books hobby, not as much efficiently in the reading books hobby. But yes. Okay, so let me just think about this for a second. Because where should will I ever encounter? I will only ever encounter strings I don't control in string literals, that I don't support yet, and character literals here. So this could be just a matter of replacing. I don't have to handle very complicated things because, oops, is no replace? Ah, replace, there we go. So this should be just a matter of replacing backslash with that. That's the correct amount of backslashes, I think. Let's try that. I am a bit in the mode where like I stack new things on top of one another because I was debugging the while loop that I couldn't write. So let's try. Let's do this again. Let's have a look at the dot file. It is now escaped, which means if I generate a dot file here and I reload this, it is correct now. Okay, so now we do have 0 is the result of read int, 1 is the result of calling the Fibonacci function. We write in with register 1, we put \n in register 2, and then we write that character and we return. That hasn't changed. Now, one thing that has changed is that in the loop here, we do have a subtract of 21 by 22. We do have the n minus 1 that we had forgotten earlier. I want to believe is that the correct value, or did I mess up? Do I have an off by 1? That is off by 1. So we need to probably fix this, probably. Do this. Do this. And I think that is correct. Let's try on 19. And now that is immediate because we have replaced the recursion with a while loop, and the while loop compiled correctly on the first try. I'm extremely happy about this. Okay, that is... Whew! That is a lot of progress this evening. We've added built-in functions. We can now write characters. We can write ints. We can read ints, and we've tried loops, and we fixed bugs in the if-else. That is starting to look like something. We still don't have structs. We still don't have strings. There's still so much missing. But that's progress. Let me commit this, and I think there's one more thing I want to address, and I'll be done for the evening. So first, let's go commit this. Export fix unescaped backslashes in dot export. Generation add assign C instruction. The write character function. And there we go. We are at the point where now we can start actually testing programs that operate on int. Whew. So next time, I think a big push would be to try to do tests, because there's very little test at the moment because I was waiting to have a proper pipeline. We have a proper pipeline. I have no excuse. We can start putting tests and try to make sure that we can cover a lot of the code and add a new test every time we find a bug like this. Now, before I go, it's been 4 hours, it's past midnight, I need to go. There's one quick thing I want to address, and it's a bit of bad news. And I don't know when my next stream will be. And the reason for that is I've had bad health for a very long time, and it's been getting worse recently. And I might be at a point where I require quite a lot of medical attention in the coming weeks. I have more tests tomorrow. It's not impossible that I might be gone for a while. So, yeah, there might be a break in the streams. Hopefully everything goes right tomorrow and I'm back on Tuesday like nothing happened, but there is a real chance I might just not be able to stream for a little bit. I'll be back. It's a matter of when, not a matter of if. I have so much more to do. We have so much more of this project to write. I want to stream video games at some point. Satisfactory 1.2 is coming out later, and I absolutely want to stream a run. I just don't know exactly when I will be coming back. Hopefully next week, and I come back Tuesday as usual. We will see. In the meantime, it was an honor and a pleasure to be working on this. Thank you everyone for tuning in, and I'll see you next time, whenever that happens to be. See you everyone.